Hello, everybody. In this video, I wanted to continue our discussion from lecture and talk about the semi-empirical mass formula, or how, as one professor I had as an undergraduate called it, the semi-unbelievable mass formula, because it's kind of weird that it works. But it really comes from this liquid drop model of the nucleus, where we just say, yeah, we've got protons and neutrons, and we're going to try and model this as just kind of like a liquid drop of particles. Let's do 5 of each. And there's sort of a radius here, and there's some bonds here that cause the energy to be lower between all the neighbors. Potential energy is lower because of these bonds, and we just want to kind of put that together and come up with a formula that sort of models all that and see what it looks like, and then fit it to the actual data. But first of all, what are we actually modeling here? What's our data? Our data is we're just looking at the masses of the nuclei. Remember in particular that from relativity, we had this equivalence between mass and energy. So we said you could think of mass as one kind of energy, or actually another way to think about it that's perfectly valid is that you can think of energy has mass. When you observe the mass of something, you're actually sort of really observing the total energy of that system. And it's just that usually most things that we observe, by far the vast majority of their energy is in their mass, not kinetic energy or anything like that, because we're not usually looking at things that are relativistic. But in the case of the nucleus, the potential energy change going from sort of these things being separated to being together in a lower potential energy state is such a big change in energy that it's actually noticeable in the mass. And so you can notice, for example, that if you have just 2 protons and 2 neutrons together, that's a helium nucleus. If you look at the mass of a helium nucleus and compare it to the mass of these things separately, the helium nucleus actually has a slightly less mass. And that's true for all these nuclei. And so that's what our actual data are, because atomic masses are some things that can be measured. And so what we're actually looking at is we're looking at the mass of the nucleus, in particular as compared to the mass of the individual protons plus the mass of the individual neutrons. Remember, Z is just the number of protons, N is the number of neutrons. And we're saying that the mass of the nucleus will just be these two, but minus what we call the binding energy of the nucleus. And here, to get everything in mass units, I'm going to divide by, this is the energy, but I just divide by c squared. There's a factor there. And so we're basically going to come up with a formula based on this liquid drop model for what this binding energy should look like. And that formula will have a few unknown parameters in it, and then what people do is they just fit that to the data of what all the nuclear masses are. So what are the important parts of this liquid drop model? I want to keep the picture. There's going to be 4 terms that historically people use with this in the binding energy. And notice here the sign. It's got a negative sign over here. So that means higher binding energy means lower energy in the potential. It means things want to kind of bond together. So you can think of it as sort of the amount by which a bond or whatever is happening lowers the energy. And so the first term here is what's called the volume term, which is just saying that if you're given a certain number of nucleons, of particles, then the number of bonds here, if they just bond with sort of their neighbors, I've drawn it as sort of a mess, but if you think of it as just sort of a more regular pattern, you can see that the number of bonds is basically just proportional to the number of particles. And remember that our letter for the total number of particles, Z plus N, let me write that up here actually, blue is red. So A is just Z plus N, total number of protons plus total number of neutrons. And so what's called the volume term is really just the volume is, and since each particle takes up, we're thinking of it as little liquid drops, and so each particle just takes up a little bit of volume, and so the total volume is just proportional to the number of is just proportional to A. So volume is proportional to the number of particles, and the number of bonds is proportional to the number of particles. And so our volume term that just expresses like, okay, we lower our bond energy, or sorry, the bond energy is mainly due to, here's some unknown coefficient that will fit, but it's basically proportional to A, the total number of particles. So that's it. That's the first term. The next term, though, is called the surface term. It means, okay, well, we've actually overestimated a little bit because, yes, the total number of bonds is proportional to the number of particles, except like this one at the surface doesn't bond to a neighbor outside of the nucleus because there you have the surface of sort of the drop. So there's sort of a surface term to correct for the fact that you can't bond to things that aren't there outside the nucleus. And so that's going to be the opposite in sign, because we've overestimated the number of bonds here. We have to subtract off a surface term. We're going to have a coefficient that again will fit to the data. And then something that's proportional to the surface area. Well, we said if A is proportional to volume, volume's radius cubed, area is radius squared. So that means this should be proportional to A to the 2/3 power. And so that'll be, so the area is proportional to A to the 2/3. So that's it. We've done two terms already, very quick. So volume term, surface term, and so that's just basically counting up the bonds and saying how those should work. But there are a couple other, there's actually 5 terms. Sorry, I think I said earlier 4, but there's 5 important ones. Another important interaction is actually these things are charged, or at least the protons have charge, and they repel each other. So that's fighting against this. And so that'll have a negative sign as well. That means, yeah, we've overestimated how much these things want to bond together. We need to correct for the Coulomb repulsion of just all these positive charges pushing against each other. So that's called the Coulomb term. Unknown constant, we fit to the data. And that's going to be proportional to, it's basically just, remember, the electrostatic force between two charges is just some constant, and then it's, Q1, Q2 over R squared, where Q's are the charges and R is the distance between them. And so the number of charges here, we're just talking about the protons. And so there's going to be a Z times a Z. We're going to have a Z squared over something that's like R. And here we're talking about energy, actually. So force is over R squared. Potential energy is Q squared over R. And if we said A was proportional to the volume, then the radius is like A to the 1/3 power. So that's the Coulomb term. 2 terms left. I don't know if I'll have room quite to written this a little smaller. The remaining 2 terms, and actually maybe I'll write them even in a separate place. The remaining 2 terms are actually quantum corrections. So nothing we've done so far is actually quantum mechanics at all, really. We've used this liquid drop model, and we've said, yeah, okay, volume, the number of bonds is volume, then there's surface correction, and then we have this electromagnetic term. But there are 2 other important terms to kind of explain some of the more detailed structure that we saw of, like, why do things kind of come in, why do stable elements kind of go along like 2 in each direction? You get this weird zigzag line. So the next 2 terms in this equation are trying to account for like a quantum structure. So those will take a little bit more explaining. So let me clear this actually for now. We'll write this back up in a minute. But first, there's what's called an asymmetry term. So the asymmetry term is basically a term that's proportional to the difference between the number of neutrons and the number of protons. And why is there an asymmetry term? It's because we're actually, again, we're going to use this particle in a box model. We're thinking of the nucleus as a box which contains protons, and I'm going to draw it separately, but it's the same box that contains neutrons. I'm just drawing separate diagrams. And the idea is, again, like we've talked about, there's energy levels in this box. Now it's not actually, the potential energy is actually much more complicated than this because we have to deal with the strong interaction. So we don't really know what the energy level spacing is, but we know that there's going to be some kind of energy level spacing. So that you're going to have, and then we also know that protons and neutrons have spin, which means you can get 2 particles per energy level. So you're going to have energy levels, something like this for protons, something like this, maybe not quite the same for neutrons. Well, actually, the idea is they should be pretty similar, actually, between protons and neutrons. Because there's very small difference in mass. They have almost the same mass. And if you remember that when we looked at energy levels, the main difference between protons and neutrons is just the charge, but we're not, what's really important for this is the strong force, which is much stronger than the charge. So these energy levels, in theory, at least look fairly similar. And so the idea is, of this asymmetry term, is just that, okay, we've got 2 protons, 4 protons, 2 neutrons, 4 neutrons, is that the idea is that the nuclei much prefer to have sort of a balance of protons and neutrons rather than have something like, this. This is the same number of particles, 8, but this is with 6 protons and 2 neutrons. That's very unbalanced. Where you have a bunch of particles kind of in high energy over here, and yeah, it's compensated a bit by the low energy over here, but if these energy level spacings sort of increase as you go up, then that doesn't even really work out. So the idea is that there's an asymmetry term here, where the preferred lowest energy state is actually where these things are more balanced. And so what does that term look like? So the asymmetry term, once again, there's some unknown constant that you fit to the data. And it's basically proportional to this different, actually squared. Because we'd want it to be basically minimized when this is 0 and then larger for any non-zero value. So we really square that. And then there's, and so it turns out, and we want to write this in terms of A and Z instead of N and Z. We could write it either way, but it doesn't, and if we remember that A is N plus Z, then that means N minus Z is equal to, another way of writing that is just A minus 2Z. This is the way you usually see it written. As you see, the asymmetry term is there's some unknown coefficient. There's A minus, rewrite that, A minus 2Z squared. That's just the difference between neutrons and protons. And then what's actually important is not the difference, but sort of the fractional difference. Because it's much more, the idea is that it's much more unbalanced. Like if you just have rather few nuclei and have like 6 there and 2 there, that's much, there's there the imbalance is 4 protons. This is a much bigger deal than perhaps the same thing than if you had like another 80 particles down here, where they were like, then the difference might be 84 protons versus 80 neutrons. That's less of a big deal. So there's just this divided by A, the total number of particles. And that's the asymmetry term. That's one of the quantum terms. The other quantum term is called the spin pairing term. And that really is just an expression of that. Remember that spin is some kind of intrinsic angular momentum that these particles have. These particles actually have a magnetic moment. They're like little magnets. And so they're little magnets pointed along the direction of the spin. And so magnets prefer to be sort of like paired up. Like so that you know, if you have like a north and south pole, then it sort of prefers to be paired up next to one that's like north and south, opposite direction, because opposite magnetic poles attract like that. And so there's a term that expresses sort of just the overall balance of spins, just in terms of how many of each particle there are. So what does a spin pairing term look like? It's basically, it's written in kind of a different way. It's written as basically just this term, but where basically just a constant, where it's let's see, it's positive if you have even numbers of both sets of particles. So if like if your protons are all paired up and your neutrons are all paired up, then you get some nice positive number here. If you've got a mix, so let me actually write that down. If Z and N are even, I kind of ran out of space there. It's 0 if you have one of those is an odd number and one is an even number. So if one of the two, like if the protons are all paired up but the neutrons, there's an odd neutron left over, then you get a 0. And it's negative if both the protons and the neutrons have a leftover that is unpaired. So N and Z both odd. So it's basically just an overall little correction term that accounts for the fact that these little magnets, and so if you want to think of them that way, like to line up in pairs, and that if you have a sort of an odd one left out, it contributes some overall energy to the whole thing. So that's all 5 terms of the semi-empirical mass formula. So let me just write it out in green at the bottom here. So we had the volume term, the surface term, the Coulomb term, CZ squared over A to the 1/3. The asymmetry term, which I've basically just got up there, A minus 2Z squared over A. And then this pairing term, which really just depends. I sort of write it as a function of A and Z, but it really just depends on whether they're even or odd. It's not a very complicated function. And so then the idea is we just take these sort of unknown coefficients, this lowercase a sub v, a sub s, a sub c, a sub a, and this delta naught, and you just look at the data and you do a fit. You just try to do a multi-parameter fit to the data. And so historically, this is what people have done. And the data are complicated. This model isn't completely perfect, and so people sometimes get slightly different fits depending on which particular data set you trust the most and what you look at. But you get values for these things of around, and you can find these in your book somewhere as well. Whoops. I'm just going to round off here. Actually, you should probably look up if you want to use more numbers. But for example, for this volume coefficient here, this a sub v, is usually around 15 MeV. So I'm going to write them out in MeV. The surface term, sort of 17 MeV. The Coulomb term, like 0.75 MeV. Notice that's relatively small. This asymmetry term is actually a big deal. It's 93 MeV. And then this delta term is usually something like 12 MeV if it's, plus, can be plus, minus, or 0. But you basically plug those in and you can find out the total binding energy of a nucleus given A and Z, sort of the total number of protons and the total number of particles. And using this, you can kind of then start to explain why certain things are more stable than others. In particular, this asymmetry term, if I flip back Why do heavy nuclei prefer more neutrons? Um, well, it's basically, if you have this asymmetry term, which seems to say that they should all balance out, but we do also have something that disfavors protons and doesn't have any effect on neutrons, which is the Coulomb repulsion. So it's basically Coulomb repulsion. Once you start to get large numbers of protons in the nucleus, this term actually starts to become significant, and it pushes things to be a little bit more neutron heavy. And then the reason that you see often these stable nuclei, especially early on in the periodic table, kind of going up and along to the right in steps of 2 at a time, is because of the pairing term. That kind of stabilizes nuclei where the protons or the number of protons or neutrons come in an even number, and so those tend to be the most stable configurations. So we can talk a little bit more about what to do with this formula and some of the interesting things you can do, but I'll leave that for a lecture, and I'll wrap up, and thanks for watching.